Welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Professor Jamie Paik, who is the director and founder of the Reconfigurable Robotics Lab at EPFL, Swiss Federal Institute of Technology in Lausanne. And she's also a core member of the Swiss National Centers of Competence in Research in Robotics, so NCCR Robotics. So in her lab, research typically leverages expertise in design and advanced manufacturing toward reconfigurable robotic platforms, pushing the physical limits of materials and mechanisms. And the particular recent research efforts are in soft robotics and self-morphing robogamis, or robotic origamis. Those are very exciting and transform autonomously planar shapes from 2D in 3D. As you've seen in the bio, she has published in a number of important journals, but also she has been part of nice spin-offs, and the latest robogami she developed in her lab was part of Mercedes 2020 concept car, which was presented at CES 2020. Today, Jamie will talk about reconfigurable robots for real intuitive interactions. And this is a very exciting topic, and also it's an extended version of what she will give, of the talk she will give at ICRA in 1 week. So we're all very excited to hear more about that. Go ahead, Jamie.
Thanks, Joelle. Thanks, Emilio, for the invitation. I'm very happy to give this talk online to our international audience. I have a couple of my students here too. So Kevin and Sarah, if you see a couple of questions online that you can answer, please do feel free to answer those questions, burning questions along the way. Today, I want to talk to you about where I come about with my lab's name, Reconfigurable Robotics, tongue twister for a long time, and why I think the achieving softer human robotic interaction is important, and why that still excites me for the past ever since I was at EPFL, and what kind of robots have spun out from that research interest. To us, I mean, robots been developed in classical environments are where the industrial revolution started, really. And this has been really the core essence of where robotics have come about in terms of their main challenges. How do we make our robots do better things than humans in a more safe, in a highly predictable environment? In that place, it was important that robots overperform humans in a sense of mechanical way. So augmented performance that compared to humans, in terms of force, speed, precision, was very important. Now, fast forward 2023, while these augmented mechanic performance is still very important, we are living in a real world environment where things are not very predictable. Therefore, it's not easy to program. Therefore, it's not easy to control. In that case, how do you determine which robots are better suited? Which robots are actually an improvement from previous versions? Maybe we need a different types of metric than just augmented performance. Maybe it can be just augmented performance, but in terms of interactivity. So having robots that are more adaptable to this random environment, robots that are more reconfigurable to unknown circumstances and unknown topology of the environment, and still being safe during its operation, may be a new metric that we can employ on top of the augmented performance. And this has been the question for a long time in my work. First of all, it's very difficult to create a benchmark to measure this. How do you know if your robot is more adaptable than another robot? Especially when your body configuration is completely different. How do you know if your robot is safer than another option? How do you know that? How do you measure? How do you compete? So these are the driving factors for a lot of our research at the Reconfigurable Robotics Lab. That being said, we have a lot of different types of robots, different formation, different sizes, different power usage, different degrees of freedom. But what's always very consistent is they're super unique. And that makes ourselves, always full of challenges. So since I do have a floor to myself, I will give you a little bit of a plug-in for our robots. A little introduction to our robots. If I can play the video, obviously that one's not working, so let me go to the next one. So we get a lot of inspirations from origamis. Origamis are known to be a versatile platform that is normally quasi 2D, meaning like a piece of paper, cardboard, or very thin substance. And we get this inspiration by having this quasi 2D substrate, manufacturing in quasi 2D, and using that to create multiples of different configurations, just like the paper, folding a paper. So when you are folding a piece of paper into multiple different configurations, and if you fold it long enough and then very precisely enough, you can create something like this, a rhinoceros. If you are not as dexterous, you probably can at least fold up a piece of airplane or a paper boat. And imagine, obviously this is multiples of pictures put together to create an animation of a rhinoceros popping up. But what if we have a platform that is automated through our robotic technology? Meaning if you were to have a core robotic component in all different layers and bond them together and be able to control every single fold, maybe we can create a foldable robot that can not only create a folded rhinoceros, but also a paper airplane if it's necessary to shift outside a screen. And one of our, the simplest robots is called Tribot. It's manufactured exactly this method. What you see on the left top corner is a 3 surface, a tripod that is self-folding into a tripod that advances forward by pushing it, employing an inchworm locomotion motion. So on the flat terrain that's very smooth, you can push forward and retract the back leg, and moving the both foot, you can create different levels of friction to advance forward. But what if we give it an environment that is different? What if it has a higher slope and it's no longer flat and smooth? For example, rough terrain. Well, it needs to adapt foot shape, and it's changing its actuation sequence of the actuators. And when you have a slope of 10 degrees, it will still roll over. What if you give a bigger challenge or a different environment again? Well, you introduce an obstacle, you can actually hop over. Again, very simple mechanism, very simple robot, but by changing its actuation sequence and changing its configuration of the foot motion, it is able to adapt to the environment. And that's what's quite unique about Reconfigurable robots. By changing its configuration of its morphology of the foot shape or anything else on the body, it's able to achieve different tasks, whether it was known from the beginning of the conception or not. And what makes it more exciting is that these robots actually can remain simple, but you can customize all the agents and more, and then the strength comes in numbers. So more of these robots you have, we can start playing with the morphing of a swarm of these robots. So when you talk about swarm in robots, which is not what my lab is focused on, but we are able to create hardware platforms that can be used to study bigger swarm groups. Now, obviously, there's a radicals group at Harvard who's done the killer robots. So we have not made thousands of these robots, but this is a first time case study of a platform that can create multiples of locomotive motions. We're creating 3 distinctive locomotions, an additional 2, so a total 5 different locomotive modes, depending on its environment and depending on the communication. So current version of Tribot has transceivers and then and the receivers to gather information of its neighboring agents. So it's able to currently communicate collect data, and manipulate objects alone, as well as its neighbors. And hopefully achieves its goal regardless of the environment or how tough the environment may be from the beginning of its journey. The take-home message here is that even if your robot is small, but if you have numerous numbers of them, you can achieve larger task field. And how do we manufacture them to be so many? Well, we rely on this quasi 2D manufacturing process. Normally, quasi 2D manufacturing process in robots don't really exist, but they do exist for creating your IC chips, which is a critical component in any robotic systems or any machinery. We rely on not necessarily just the photolithography of creating this PCB board, but creating the overall shape and outline of the shape of the robot that allows us to actually embed different components that already exist and then run the final assembly. But the magic is right here, the self-folding part. If you're able to create a self-folded robot into a three-dimensional robot, the magic or the difference in changing of the dimensions allow you to create three-dimensional movement. That means three-dimensional task. Changing of this dimensionality allows us to not only create such a large design space, but also such a large workspace that the robots can achieve. And that really allows me to talk about sustainability. Sustainability is such a huge word in anyone who's doing anything in recent years, not just because we're talking about how to preserve the environment, but it invites us to think about how are we approaching our level of studies in a more sustainable manner. To me, having a sustainable platform for robotic manufacturing is that we produce what's necessary for the application. If the application necessitates us to have additional sensors or different types of motors, this quasi 2D manufacturing platform allows us to have that. How? Well, basically, we're following this conveyor belt of the materials, cutting processes, pressing, pick and place different components, and assembly at the final end. By having this quasi two-dimensional manufacturing platform allows us to insert different versions or different processes in between, as long as it's within this work field, within this dimension. If you look at on the application side, application will allow a request and it demands you to have different types of components. That can be used as a customized file to update the system design. The system design is with the different parameters. It's not quite completely new. These are the same type of libraries that we use for 3D printing. 3D printing really has sort of revolutionized design packages to be completely compact, readily readable for regardless of which type of CAD program you're using. We could add additional step there for manufacturing fabrication sequence. And that sequence will allow us to actually create and complete this manufacturing process. And that is quite exciting for us. And don't just take my word for it, but based on this manufacturing process and methodology, we were able to update and iterate our design multiples of times beyond what I was willing to sign up for. And that's when we were working with Mercedes-Benz industrial designers who were requesting us to update our flap design for the concept car to be presented in 2020. So that meant us having to reiterate the flap design, I think about 50 times over the course of a couple of months. And that's quite unheard of in terms of creating any hardware, let alone robotic hardware. So what we actually ended up producing was having a quasi 2D platform that creates a three-dimensional motion. So I will go more in detail what this kinematic chain is for the bottom plates example here. I don't know. Can you see let me see if I can have my cursor.
We can see it. We can see it.
Can you see my cursor moving?
Yeah.
Perfect. So the top surface actually moves in 3 degrees of freedom, meaning it has a translational, Z direction translation, and 2 rotational degrees of freedom. What we had to update was these flap angles and flap length, so that we can allow it to, this flap range of motion to be optimized for the size of the motors. We also had to take into consideration if we can optimize the height that it gets popped out of the foil here. So we installed 36 of these modules on the back of the Mercedes, and then this is how it looked at the end of our 6 months effort. Hello? Hello?
Yes,
Okay.
I can hear you still.
Perfect. Right.
Yeah,
So
can you hear me, Jimmy?
Yeah. Can you hear me?
Okay.
Yeah.
Yeah.
So what you see here is a popped up foils that are moving at 3 degrees of freedom. And as you can see, they're completely embedded behind the airfoil zone of the car. And that was the result of basically 60 times of iteration of the foil length, the panel range of motion, as well as the overall height change during this period. There was no new sensors added, but the transmission length change actually costed us a lot of iterations and manufacturing process as well. The next thing I want to talk about is, yes, we are inspired by a lot of folding joints of the origamis, but what if we can expand this design space, meaning any type of robot is just as big as its initial materials? What if you can add materials or subtract materials, like in Lego blocks? So more the Lego blocks you have, more of the freedom of the creativity you would have, and larger the workspace, design space would be. And this type of idea was carried on for our European Space Agency project. So the idea was having a single Lego block, a homogeneous shape, and having that to be the base block to add more or subtract the number of blocks. And depending on how many blocks you have, and because they will be independently controllable, we could create an explorative robot that can explore underneath the ground, over the ground, and above the ground. And because if it's space, we would have space astronauts who's working in a space station. We thought the same platforms could be used for fixing the solar panels, or used for exploring and testing different specimens, serving as a third arm, or used as a platform to interact through a tangible medium with people on the ground or anyone else that requires to have communication. And for me, this was quite exciting because we're not taking the essence of multiple folding joints away, but we are adding and subtracting them as we see fit for different applications. So combining origami and modularity really played a huge role in the next project. We call this a MORI, modular origami. So having the geometric flexibility of origami robots and functional versatility of modular robots allows us to really expand this design space, as well as overall volume and configuration of this robots. And what can you possibly achieve having this both flexibility and versatility? Well, immediate thing you can always go for is quad pad walking. That's a lot of robotics that work on quad pads. But if we can have enough of modules that allows us to achieve this quad pad walking, the next thing that we often go for is manipulation. How about two-fingered manipulation or two-legged soccer player? But also creating a different box shape by reconfiguring its location of attachments. So having a fluidic flow or a dynamic flow of placing a different object from one end to the other, translating it, manipulating it, reorienting it, it really depends on how we are controlling this individual modules and its relative position to its neighboring modules. And this is how we came up with Mori, or this is how we first imagined Mori to be. And this was one of our first generation Mori. So this is Mori 1, where a single module comes with 3 degrees of freedom, 3 rotary degrees of freedom on each edge. So what you see on the left top hand is a flat Mori that goes across from point A to point B. What's exciting about this module is that this is the smallest unit of polygon. So more the polygon you add, whether it's active or passive. So if you add dummy modules, what you see on the left bottom and the right top, you have dummy modules that are attached to the sides of this active, the Mori, and that creates a different workspace. You have the same number of modules, but you have a different workspace. But if you add another module that's active, you're able to create a bigger workspace again. So because of this geometric relationship that couples one module to another, this is the relative constraint, or this is a relative advantage for creating the specific workspace. But what if we can actually control this again? Meaning, how about you're taking advantage of not the geometric versatility here, flexibility here, to enable it to be even larger? What do I mean there? Well, what I mean is when you're doing meshing, calculative meshing of any structures to understand structural mechanics, you break down to the smallest unit as well, again, in polygons. And in that case, we create a mesh of the solid or shell model and try to understand the relationship between the modules to each other. And then we calculate for the individual modules. And here, not all triangles have equal length. Well, the reason is that we are going for the high density, highest structural difference in those specific zones. But if we can have mechanical version of it, maybe we can actually recreate this simulation or structural mechanics simulation in real life. And that's exactly what we aim to do with Mori number 3. So Mori 3 looks similar. It's 3-edged modular robot, but we are actually changing the shape. So from equilateral triangle, where all 3 lengths are equal, we are extending its edge length or changing relative edge length. And that allows us to actually have a different angular relationship from one edge to another. This is basically going up about 1 centimeter, so it goes beyond about 20 to 15% from its original length. But this small change completely changes how we are able to control when these modules are completely assembled. So quad pad. Imagine if we actually have to have a quad pad that allows us to stand out from the singularity point, which is completely bottom, and advance forward. Currently, we only have 1 backbone here. So currently you have 1, 2, 3, 4, 5, 10 modules assembled next to each other. So you have 1 backbone with 1 backbone, which is sharing by one length between the modules, and it's advancing forward. If you were to use isosceles triangle, equilateral triangle, where all the lengths are the same, you would require at least a 30% more number of modules to achieve that, because you won't be able to have that changing length in backbone as well as this relative length. Same idea with a robotic arm here. So currently we have 1, 2, 3, 4, 5. We have 5 modules here. So basically 1 2-legged side of the quad pad. You're creating a hockey puck passing motion. What's important when you're tossing around a hockey puck is that your arm has to remain completely parallel to the hockey puck and perpendicular to the surface, and then parallel to the movement of the hockey puck. That ensures your smooth passing motion. So it's a bit difficult to see from this angle, but we are able to achieve this motion again because we're actually extending a couple of the modules edge length here. And that allows us to, again, maintain same number of degrees of freedom in the edges, but create this larger range of motion in the workspace for our effective usage. Best way to go from point A to point B in a smooth surface or rough surface, for that matter, is just rolling over there, rolling over with a wheel. Well, it's difficult to achieve a wheel pattern or wheel rolling motion when you have modules and not enough modules. If you were to have about 10 times more modules, it will become enough of a smooth rotational radius that you can roll over. But in this case, you're actually pulling one module over the other to create this rolling motion. And here too, we are using edge extension to allow us to showcase this. Another exciting part is that here is that because we can change the edge extension rate and directions, what can we do? We can actually control which direction we're rolling it over. So we are trying to go left, right, and straight by employing different edge length. You see the modules are also tethered here with wires, but technically we are able to use onboard batteries to achieve this. And the latest work that we're working now, we're showing the QP controller to optimize different range of motions. We are demonstrating it without the cables attached to the batteries with the current experiments. So I want to come back to the idea where having having multiple degrees of freedom and folding joints allows us to have a larger design space, and having a larger design space allows us to have stronger and more intuitive interaction. And that's because we have more degrees of freedom to work with. And that's what I want to get back to you about here. So dynamic and soft robotic interfaces, or TR, the tangible reality, is quite exciting topic for our lab, because this is a reality environment where we don't have much other choice. Currently, how we interact with the virtual world, how things are portrayed to us are completely digital and completely visual or auditory. So on screen, as you're watching me now talking, is that you're hearing me and you're seeing me giving you a talk, but you can't really feel like you are in space, in presence completely, because you're not completely immersed. And even if I were to show up in front of you in a holographic image, probably you won't feel too immersed. The reason is we feel a lot through sense of touch. So how do we feel and what we see? Well, when you see something, you want to feel it to get the sense out of it. And when you want to get a sense out of it, your skin works really hard with a lot of mechanoreceptors on your skin level, gives you the feeling of temperature, pain, stretch, as well as pressure. If you want to tell robot or interface to transfer this information, the sense of sensation, without me touching the reality, but having a digital or mechanical platform that recreates this information digitally, what do we need to send digitally over? Well, first of all, you have to know what the capacity of platform is going to be. Is the capacity of platform going to be real enough for it to recreate what I'm sending over? Well, so let's forget about what the capacity of the platform is, but who's going to first feel it? Well, I can tell you, I picked up this Coke bottle, and it seems like compared to a couple of years ago, the PT bottle got much thinner because I'm like squeezing it, and this Coke's been sitting out for a while, so it's a little warmer, but that's very relative. So we might want to tell a robot to feel it first and tell me how it is. So that's verbal. So that's the first challenge. How do we first gather enough information here? That's first challenge. How do we gather enough information? And second challenge is, what do we transfer over? So let's attack the first part. How do we first gather information? Well, if you have a camera, you will tell you the Coke is there. This is about how big a bottle is, and tell you what it is. But it can't tell you how thick or thin the bottle's PT film is, and it cannot tell you what the temperature is. Maybe you can do the temperature sensing through optical sensor, and then you can have a robot having the low sensing to feel the outer parameter. But that's not what exactly is conducive, because we don't know if it's enough, because we don't necessarily have a very accurate temperature sensor. We don't necessarily have a very accurate sense of touch, because I know because people cannot say this is 1 kilo or 500 grams. They know it's just empty or not. So it's not that straightforward. How do you make this? How do we transfer this information? It is transferring this information and gather this information. So the robotic touch current state of art is really very much vision-based. Through vision, we can do a lot. By looking at the optical sensing, you can see from the changing the optic fibers, radius curvature, you can sort of see how transparent the materials, how hot or the temperature of materials, and then how soft it is as well nowadays. But at the end, they are quite nonlinear, and we have to go through a lot of learning to make sense out of it. And if you want to talk about slipperiness, stickiness, softness, for example, if you have a soft tissue on top of a hard surface, this feeling to this feeling, like if the softness is underneath, if this feeling, it's completely different for us. But when you're putting this under load cell, they measure the changing of the displacement compared to how much force you put in. It's going to be the same reading. So it's not straightforward. So that's the first. I don't have answers just yet, other than extremely better sensors. But that's the first challenge. Second challenge is, how do you recreate that feeling? So let's go back to how we feel it. Well, we feel it through two different ways combined. One is cutaneous feedback, meaning the skin deep. So my skin with the mechanoreceptors feel a lot. And kinesthetic feedback, which means I actually want to like knock on it, squeeze it, hang it, like toss it around to get the feel out of it. So humans use both of these feedbacks to learn what the environment is. So this is where my research goes. How do we create platforms hoping that sensors can give us enough information, and the robotic manipulators can give us a lot more information in the future, to have a platform that can recreate these feedback? And currently, they are divided into multiple scales and multiple scales. So skin level, cutaneous feedback, as well as kinesthetic feedback. Because skin level cutaneous feedback is such a very thin surface, the size and compliance of devices have to match the compliance of the skin. Kinesthetic feedback is really about the movement of hands and movement of your body. So your device has to match the compliance of this movement. So that's why the scalability is not just about the sizes, but also about matching the compliance. So one of the things that we're trying to use our platform, Miros, is to match the compliance of our larger scale interaction. Larger scale interaction meaning your full body. So about 100 kilograms maximum load on one of these platforms or two of these platforms would allow a person to use their kinesthetic feedback of their muscle joints and the muscles. So this also creates 3 degrees of freedom, vertical up and down, and 2 rotational on the XY axis. And that, with that platform, what we're able to achieve is this type of simulation. So it's fun game, but it's not just fun game, because what you're seeing here is an interactive platform where the user is feeling what they're seeing. It's the first time of its kind to actually be interactive with the physically interactive with the virtual environment on it. So you can think about like glorified kart track simulator, but it's more than that. Imagine you don't want to be standing 2 foot on the board, but you're doing a skiing. Skiing simulator will require to have actually 2 legs having different motions. Well, if you're good, that's quite straightforward. But if you're not good, you end up having 2 legs in the different directions. So with the 2 of these platforms, you'll be able to achieve that one separately. So having to figure out this network of stiffness change changes in the platform is currently what we are focusing our research group on. I was telling you about the scalability. The smaller and more delicate level of cutaneous feedback really comes from the skin level. So let me talk to you a little bit about the interactive soft pneumatic actuator skin. The soft pneumatic actuator skin is really the skin that you can wear on directly on your skin, which does not interfere with your actual motions. So it won't interfere with your kinesthetic feedback, but also your interaction with the objects that you're manipulating. But the skin is there to give you enough of feedback, the additional augmented reality feedback. Think about the augmented reality glasses that you're putting on your eyes, where normally you see everything straight, but you have augmented reality objects that's floating around with numbers and objects. Same thing here. You're getting an augmented sensation of objects that you're currently touching or not touching. So currently the experiment's been done directly on your skin on their fingertips, but if you're prosthetic users, these skins can be attached elsewhere where you have still the sensation left. These sensors are also embedded with their own sensors. So the skin has its own sensors that allows us to feedback loop control what it's actuating for, as well as the contact forces and its locations. These sensors were also developed EPFL by Professor Lacour's group. They are completely integratable to the skin through liquid metal and very thin gold film. And then if you make enough of them side by side, you can have a grid patchwork where you can create not only the Morse code, Morse code, but you can distinctly show the location, shape, pattern, and beats and frequencies that can give a lot more intuitive sensation and information directly without relying on your vision or auditory means. And I think I'll skip next couple of slides because I wanted to aim for 45 minutes. So this is our foldaway. It was a little. This was our first version of 3DOF haptic joystick. So this is a much smaller version of mirrors that you saw before, which we developed for skiing or snowboarding simulator. This is for giving a single point feedback to recreate profile in a stiffness change upon the profile changes. So when you have this embedded different material properties of these picked up objects. So if you were to pick up the cheese at the back, because we're in Switzerland, it's good to have a representative food group there. You would actually feel the change in curvature to feel the edges of the cheese block as well. And if you were to navigate through a screen, an image, now you no longer have to rely on the video image, but you can also use a cursor that also serves as a feedback device to give you a different material density what's represented in the visual image. Same platform can not only give you feedback underneath your fingertips, but can be used as a wearable, as a extensive extension of one's body. So this is a work that we work with Sylvester Micher's group at EPFL, who's studying the effectiveness in controlling the limbs that's beyond us. So their work comprises of having an additional finger, but here we're showing the third arm. It's not necessarily built as a prosthetics, but to be a helping hand when you just need the extra hand when you're soldering that extra wire or picking up the key that just got dropped when you have a Coke on the one hand and the other hand sort of filled with other soldering iron. And on the right-hand bottom, you can see we can potentially use it to pet an origami dog as well. The take-home message in these slides is that because these origami platforms are so light and so versatile as well in terms of their range of motion, we can use it as an interactive device for a manipulation as well, worn on your body or as a desktop. And then this one shows the different versions and different scales. So on the right, on the left top, you see Mete wearing it with the 2 modules in series, controlled by his breathing to match the image on the screen. And then the smaller version, the fingertip versions on the right top. And then the right bottom, you see them connected in series rather than in parallel, connected in parallel rather than in series, as what you see on the left top. So some of these works are featured on these magazines, but I encourage you to read one of our initial works on Nature Machine Intelligence that really talks about how we are using this as a joystick with a haptic feedback. And hopefully I convinced you today that these origami-inspired robots with modularity and reconfigurable mode can have multiple application and communication through tactile means, wearable in terms of having a third arm or having a physical, cutaneous, and kinesthetic feedback, and being collaborative as multi-agent swarm robot platform. And I didn't really talk about the medical robots, but I will be happy to answer any of that question during the Q&A period. I must mention our funding bodies, and if you have any more questions, I'll be happy to receive them now. Thank you.
Thank you, Jamie, for the great talk. Let's open the stage for questions. You can either write in the chat, and I will read them for you, or you can also just unmute and ask.
Jamie, okay, I will start. First of all, very impressive. Thank you for giving this talk. It's very interesting to see all the different applications that you're coming up with and different technologies. Now, if I may ask a little bit of a provocative question, okay? And the following. So it is very usual to find people who talk about robotics and they look at bio-inspired robotics and animal-inspired robotics, your robotic cheetah, robotic spiders, robotic, whatever. Right?
Octopus, fish.
Yeah, right. So you see all those things, right? I was wondering about the opposite. So you talk about origami, right? Do we see this in nature? Or this is something that you're developing mostly because we think that, or the sense that I got, especially at the beginning of the talk, is that it's something that facilitates the manufacturing process, right? So it's easy to print gazillions of these things, right? But this is something that we see in nature. So it's kind of like a reverse, right? So
right. No, that's a good question. So bio-inspired robots is obviously fascinating for a lot of people. I'm not so sure it's fascinating to all of us because we sort of have a God complex. So we want to create something that God has made and we want to do the same, like a Frankenstein, and we don't know, making Terminator is a taboo. So we go for something else, or it's because we understand the evolution in nature really is the best way of optimizing any type of design. So I'm not sure which one is which, but those ones really were not really my background to actually mimic the nature. That was not my intention.
Right.
The intention was, how do we optimize what we have and not reinvent the wheel? And it turns out, if you can take advantage of a platform that's already smartly designed, how is it possible to not having to reproduce the same thing over again for a little bit of a different task or a little bit of a different environment? Because I actually come with a background where my thesis was on humanoid robots. So when I was displaying this humanoid arm that throws a really nice baseball pitch, everyone was like, that's really great. And then I'm like, of course, because what we did was we actually recorded the baseball pitch motion of the pitcher and then did a motion trajectory completely copied onto the 7 degrees of freedom arm. So we got the motion trajectory of the shoulder joints. We had 3 there, 1 there, 3 here. And then we had 8 degrees of freedom hand. So that platform allowed me to program the motion trajectory of the pitcher. Perfectly nice. Visually, it looked really great. Bio-inspired, great. But the problem came in when Powerball came in, if you want to do anything else than just pitching a ball, just grabbing and shaking hand was difficult because either it was crushing my hand too much. And if I did a compliance control, at that time, my control was not as good as, I was not doing machine learning then. So it was either crushing my hand or it was not giving a firm, nice shake of a hand. So being inspired by biology and nature is really great, but you can only mimic. If you want to mimic really good mimic to do a motion as well as functionality, both ends, you cannot just mimic in a superficial way. You actually have to have the motors that mimic the muscle groups, because shoulders do not only have 3 motors, it has all different tendons that's aside from the actual motor. And that's also is not rotary. It also does not have the moment of inertia that's completely lacking. It's so much faster with a higher bandwidth. So either we have to mimic all the way with having the muscles, tendons, and then the bone structure of the human, then that would be real imitation. But just being inspired, it's very difficult to recreate the functionality. So that's where I spun off and said, maybe we don't need to really rely on the form, but more on the functionality. Obviously, I'm not saying we can actually become like, I don't know, I keep making reference to Terminator, but one of the villain was like liquid metal man that dies completely, continuously falling on. We are not made like that. So that's not why I'm saying we are trying to mimic that. But functionality wise, I thought Origami platform was quite interesting because we can create so much more functionality from the same platform. And just to give you a long answer to a short question there in terms of, is there anything in nature like that? Not completely, but folding structure is in nature all the time. So pine cones, it's kirigami, it's cup patterns. So when it dries, it flares back up. And when it's completely young, as a cone, it's completely closed off. So depending on the humidity, it opens and closes down. Same thing for leaves. Leaves, when you see before it's opened up, it's an expandable structure. Same thing with bees. Bees' wings actually get folded into their back, and then when it's opened up, it opens back up. So there are a lot of folded structures that are reproducible, continuously reproducible in terms of motion. But currently in the literature or in the robotics world, we often see structures that's deployable, but not reversible. So I'm always interested in achieving this reversibility of origami structures.
Okay, thank you, Jamie. Yeah, because clearly it's not always the bio inspiration is good, right? So I mean, we could make flying things that flap their wings, but airplanes don't really work that way, right? But because like for nature, it's difficult to come up with something that looks like a jet engine.
Right.
But
I think we can always get a really elegant solution, but we haven't really got. I think that would take a lot more effort from a lot of with a different research groups in consortium. So it's not just a matter of design, just not matter of the control, not just a matter of materials, but really concerted effort to create something that's really elegant altogether. But this is where we are now.
Yeah, thank you, Jamie. Yeah, very, very inspiring. Yeah, I leave the floor to other people if they want to ask questions.
Yeah, is there any other question?
Right. Well, if there isn't, please feel free to reach out to me. And thanks everyone for listening throughout the talk.
Thank you, Jamie. It was a pleasure. And I'll wait for an okay to upload the video from your
Great.
student.
Thanks,
Thank
Joelle.
you. And good luck at ICRA.
Bye.
Take care.
See you at ICRA.
Bye-bye. See you. Bye.